Okay, so more on functions, specifically more on the exponential function. Okay, so just another little graph. We saw that in general, we have that e to the kx looks something like this. Just being very rough with this, not trying to be super accurate. Sorry, my sleeve got caught on the edge of the notebook there. Okay, it looks something like that. That's for k positive. K greater than 0. And we saw we had, this is growth, okay, and we had that e to the kx looks a bit different. This is if k is negative, it looks something like this, okay? Okay. Being a decay, okay? You know, the heights are a little bit different here, but the shape is really the most important thing. So this is growth, specifically exponential growth. And this is exponential decay. Okay, very, very important ideas, okay? Describing everything from the amount of nuclear, the amount of radiation coming from nuclear waste, or the that would be something like this one, or something like this one would be, pandemic, what we're in right now. Okay, so two very important functions. And I want you to notice something. This one is strictly increasing, okay? This one is strictly increasing. This one is strictly decreasing. Okay, and we had something about increasing and strict increasing and strict decreasing functions in a previous video lecture, which was that these are kind of special because there is only one input that will get sent to a particular output. Okay, so for example, if I set a y height here, I can determine exactly the x which gives it. So if I set my y height there, I can find the exact x that gets it. Okay? Here I can set my y height and I can find the exact x that gets it. Okay? So these are one-to-one functions. Okay? So the exponential functions what does that mean? That means if e to the k times x is equal to e to the k times y, this must ensure that x is definitely the same thing as y. There is no other way that this can work. Now, not every function has that property where I can just take out the variable like that, but this one does. Okay, and that's very useful. It doesn't matter if it's growth or decay. This is always going to be the case. Okay, and we said that one-to-one functions have an inverse, and such is the case here. Okay, exponential functions therefore therefore have inverse functions. And the inverse function that we have is very special. The inverse of y equals e to the x is called, has a special name. It's called the natural logarithm. Okay, it's called the natural logarithm, which is kind of a fancy name for a fairly simple idea. So let me give you the idea of how a logarithm works. So if, really quick, really simple, if a to the b is equal to c, then this says take a, raise it to the power b, and then the answer is c. Well, the logarithm works with the same information, but it works a little bit differently. It says I have the number a. I want to get the number c. What power do I need to do that? And of course, since a raised to the power b gives me c here, the power that I need to raise a to c is going to be b. Okay, so this is exactly the same information here and here. A raised to the b gives me c, which says if I raise a to the b, what do I get? Well, the answer is c. Well, this one is phrased, same information, but phrased just a little bit differently. It says I have the number a, and I want to raise it to a power and get c. What power do I need? The power is b. Okay, so I only ever think of one example. Okay, I actually only ever know why, but I would say this is the only one that I ever really learned, and then the rest of them just kind of make sense because I understand this basic principle. Okay, this is a really simple one. Okay, if I have 10 to the power 3, and like I said, the only example I ever really think of, this is 1000. Okay, which is 10 by 10 by 10. Okay. So if I have the number 10 and I raise it to the power 3, I get 1000. So what is the log to the base 10 of 1000? Well, what's this saying? This is saying, what power do I have to raise 10 to in order to get 1000? And I can see right here, the answer has to be 3. So 10 raised to the power 3 gives me 1000. Or if I have 10 and I want to get the number 1000 by taking powers of this 10 here, that power needs to be 3. Okay, that definition is a little bit important. Okay, so how does this apply to the exponential function? Well, remember the exponential function is like this. Okay, so if y is equal to e raised to the power x, okay, then how do I get y? Okay, well then I have, actually, yeah, this is fun. I've done this the other way around over here, but if e to the x then is equal to y, how do I get the x? Okay, well this means that the log, the thing I'm taking powers of is the base, that's e, okay? And then the thing I want to get is the y, and that has to be the power that I've put in, which in this case is x, okay? So This is called the natural logarithm, log to the base e. Logarithms in base e and base number e are called natural logarithms. Okay, logarithms in the base number e are called natural logarithms. Okay, and let's have a look at how this works. Okay, it's actually fairly simple and straightforward. Suppose I find, say for example, I have e to the x and say that that's equal to 10. Okay, and I want to find the x that makes that work. Okay, well then I know, okay, that I have the base number e, I want to raise it and get the number 10. And the power that I need is going to be the x. So this function is going to give me the answer. And generally, okay, log to the base e of some number y is also written as just ln of y. And this is what you will see on your calculator, lny. Okay. You probably have a different calculator from me, but I'll show you what it looks like. So we can see here on my calculator I have log, okay. Anything that just says log like that means log to base 10, so please ignore that. But this one here is log ln, which means natural logarithm, okay. So let's do this calculation here. Let's find what x has to be in this case, okay. Well, what do? I take the natural logarithm of 10, and that's going to be my x, okay. So all I need to do is put 10 in here, and I get the number 2.3, okay, 2.302. Okay, so now let's have a look at this, okay. What does this mean? This means if I take the number e and I raise it to the power 2.302, I will get 10, okay, or something very close to 10, because obviously this digit here goes on a very long time, okay. So let's just check that. I'll go e, I'll raise it to the power of my answer on my calculator, so my calculator has that function, and I get 10 back, okay, so that's how that works. So the natural logarithm is the inverse of the natural logarithm is the inverse of the exponential function. Okay? And what does that function look like? Well, I want to just refer again to this function. Okay, let's look at e to the x here. What did that look like? It looked like this, okay? Let's keep this image in our minds all of the time, okay? It's a growth function, okay? With this kind of curving shape that gets a lot faster very quick, okay? Like that kind of shape, okay? Does that make sense? I hope so. Okay. Sometimes I forget that there's no one in the room here with me when I'm chatting, okay? So this is my graph. This is e. This is my x, and this is y, which is equal to e to the x. Okay, so this is a graph that gives me where I take the x value and I work out the y value. Well, let's instead suppose that what I want to do, really, is that I want to take the y value and work out the x value. Well, what do we notice here? We notice a couple of things. First of all, the domain of e to the x. What does that mean? That means the allowable input number is x. That's all values of x. Totally fine, okay? But what's the range? Remember, the range is the possible outputs, okay? And I only ever get positive values of y, which means all values which are greater than 0. All values y which are greater than 0. That's not a very good y. All values y which are greater than 0. Okay, so if the inverse function is going to undo this, then it needs to be the opposite. Okay? What is that going to look like? Okay, well this is going to be a function of y, and it's going to give me an x. Okay, and I'm going to flip the graph just a little bit so you can see what this looks like. Okay, this is the x, which is equal to the natural log of y here, and this is y. Okay, and what do we notice? Before, our domain was all values of x, and our range was only positive y. Well, what does that mean? That means that this time, okay, we're going to have only positive values of y are in my domain, only positive values of y are my acceptable inputs, and my range is going to be all values of y, all values of x. So this is going to look like this. And I don't know if you can really see it, but they're kind of one tilted on the other side, okay? One crawls up and the other one curves this. One curves like this and the other one curves up like that. And it's almost like, if you can imagine, now remember that y is going up, it's the mirror image of this one here. Y is going up to the left here, y is going up to the right over here. But really all I've done is just like turn the graph on its side and mirror it, okay? And particularly, remember, e to the 0 was equal to 1, and that tells me what? Well, that tells me that if I take the natural log of 1, which is the same thing as the log to the base e of 1, well, that has to give me the power, which is 0. So this number here, that one, is y equal to 1. Okay, y equal to 1. And we have a couple of special properties that I want to just talk about for a moment. Okay, since these functions are inverse, since e to the x is equal to y, and the natural log of y equals x are inverse, okay, that means that if I take the exponent and I raise it to the natural log of y, this means take the log and then do the exponent. Well, since they're inverse, this just gives me the number I started with, okay, which is y, okay? And, on the other hand, if I take the natural log of e to the x, this means take the exponent and then take the log. Well, this one undoes the effect of this one, so that one gives me x again, okay? So that's how these work, okay? And we will, there isn't a whole lot to answer about this, but we can calculate some values, which I think are pretty important. Okay, say for example I wanted to solve for x, and we'll do an example here. Real simple one, okay? We're going to have e the 2 times x is equal to, pick a number, I'll pick 12, okay? E to the 2 times x is equal to 12. Well, how does this work? Okay, or how can I do this? Well, now I can take the natural log of both sides. Remember that I'm always allowed to do the same thing to both sides of an equation. Okay, so I have the natural log of e to the 2x, okay, is now going to be equal to the natural log of 12, okay, which is fine. But like I said, this one here is special. Why? Because the log cancels out the effect of the e, and I end up with just 2x is equal to the natural log of 12, which means that x is equal to the natural log of 12 over 2. And this is something I can do on a calculator. Okay, so what do I do? Fraction, natural logarithm, put in the number 12, put it over 2, and there's my answer, 1.242 roughly. Okay, so that allows me to solve for the value of x there. Okay, let's do another one. Okay, suppose instead I have something different. Suppose I have that the natural log of 3 times y is equal to 7. Okay. Well, then what do I do? Remember here I took the logarithm of both sides because I wanted to cancel this exponential. Well, now I want to cancel a logarithm. Okay, which means I need to use the other operation. So in this case, I want to take e natural log of 3y, and that's going to be equal to e to the 7. Okay, right, like that. But this is where we had this special property, right? E to the natural log, it just pulls out the argument here. Okay, so what do I have? And I'll do it on this page actually, just so I have some continuity. This implies that 3y then has to be equal to e to the 7. Okay, 3y has to be equal to e to the 7. So now, how do I find my y? Well, y then is just going to be e to the 7 divided by 3. Okay, and again, something I can do on a calculator. So what do I do here? I would take my exponential, which is down here. In fact, there's another one up here which I can use, which is a little bit easier sometimes. E raise it to the 7, put it over the number 3, and this is going to be quite a big number. Okay, this is going to be 365.54. Okay, so that's how logarithms are inverse to exponentials. Okay, and of course I can do this with more complicated examples, which I might do in the next video. But hopefully I've illustrated that these are opposite functions, and that you now understand how these work. Okay, thanks everyone. Talk soon.